Assalamu alaikum. Today is our second lecture of application principles and methods of nuclear tracks. In first lecture we discussed about particles, ions interaction with matter, and we did all the way up, and today we will start furthermore. And first of all, to just revise, you already know what is when particles or ion interact with matter. Let's suppose when a charged particle is moving having some mass m with some velocity v and interacts with some matter. When it interacts some matter, absolutely it absorbed by the matter, and obviously there is some loss in their velocity. So this is how when a particle interacts some matter, the energy losses, and that energy loss is known as stopping power, as we already did this stopping power in our lecture number 1. Okay, so this is the final formula of stopping power which we derived in our previous lecture, which is 4 pi e power 4 z square divided by m naught v square multiplies by nv, where E is the basically electron, Z is basically the atomic number of the material in which the particle is penetrating, and m naught is basically the rest mass of electron, and V is basically the charged particle's velocity. Okay, and n is basically the number density of the particle, and B is basically the energy. Okay, so this is we did in our previous lecture, and today is our lecture number 2, and we will discuss about first of all energy loss characterization. So what is basically energy loss characterization? Simply we can state it that basically it's basically a plot, and we name this plot as Bragg's curve. Okay, a plot of specific energy loss along the track of charged particle known as Bragg's curve. Okay, so this is basically a plot of specific energy loss, okay, in which along the tracks of that charged particle we will know, and this is a Bragg's curve. Okay, so here you can see on y-axis there is basically the energy loss, which is the stopping power, and on x-axis you can see the distance. You can see in the initial state when particle interacts with some matter, the line is linear, what it's supposed to be, because when particle just hitting the matter, initially the particles have high velocity, and after some time the velocity gradually decreases. That's why you can see first of all it is uniform, and after some time, after some distance, after some penetrating into the material, there is a bump, means loss, means high loss in energy, and there is a sudden decrease because it loses all the energy and stop into that material. Okay, which particle which just go inside. Okay, so this is basically the energy characterization, and we know it as Bragg's curve. Okay, next thing we will discuss about the energy straggling. Basically this we can say that sharp beam shows energetic behavior. Okay, if a particle have sharp beam, this is sharp, so we can say the particle is energetic. If this is not sharp, so we can say not energetic. This is basically the energy straggling. Okay, the next concept is stopping time. What is basically the stopping time? The time required, as the name stands for stopping time, so we have to stop something because we are studying the particle interaction with the matter, so we must, we must have to stop the particle or ion when it goes inside or penetrate into the material. So that's all the time required to stop by a charged particle in the absorber can be deduced from its range and average velocity. Okay, once particle go penetrate inside the material, the time which it takes to stop the charged particle in the same absorber medium, this known as stopping time. And okay, so how to derive the relation of stopping time? We will start with the formula of kinetic energy. You know, kinetic energy basically half mv square. If you want to find velocity, move other aspects on to the other side, and you will get v square, which is becomes equals to 2e divided by m. Okay, so now taking square root on both sides, you will get v, which is equals to 2e divided by m. But this is in the case of non-relativistic case, because you are not seeing any relativistic term inside this, like speed of light or any other relativistic term. This is basically non-relativistic relation. So to introduce a relativistic relation, you must have to introduce a relativistic term. So let's suppose particle is moving with speed of light, so you must have to include speed of light term, which is c. If you include c outside, so you must have to include, if you multiply with by c, you must have to divide also by c. So we divide c, but inside square root, that's why divided by c square, because c square cancels with the square root, it becomes c by c, and c cancels with c, all the equation is same. Okay, so no change if we put c in numerator and c square inside square root in denominator. So now this is the velocity of the particle, but this is now relativistic term. Okay, just put the value of c, which is 3 multiplied 10 raised to power 8. You will see your relation. And what is mc square? Mc square, you know, in nuclear physics we all know this is basically equals to 931 mega electron volt per nucleon, or you can say 931 AMU, which is the smallest unit of an atom. Okay, simply here m is the atomic mass and E is the energy of the particle in mega electron volts. We can say that the average particle velocity is now average. For the case of average, we use this bra signs. So V bra basically equals to kV. Okay, in the case of average velocity. Okay, because particle is penetrating into the material, so it must cover some distance. So that's why we use our simple basic formulas of distance. We all know that distance is basically equals to with velocity into time. Okay, so now just put because we are dealing to find the range of the particle which penetrate into the material, so we can here conclude that our range is basically equals to kv multiplies by t. Okay, because distance is basically the range, and v, and what is the v? Basically we already know kv, which is the average velocity. Now put the value of this here, k, average velocity v into time. Now this is your range, because we are studying stopping time, we have to find the stopping time. Move t one side, all other aspects on to the other side. uh, so this is your final relation. Okay, now what you have to do, you have to do here like that, this is r is your range, and this is your formula where we derive this formula is t is equals to r c k, r and k, r and k similar, and now you have to put the value of v, which is here we derived, which is this 3 multiplied 10 raised to power 8. Okay, and because this is denominator, and so this term will reciprocal, so this upside, this downside, this upside, this downside multiplies by, because we move this mass other side and this energy other side, and we will only multiply it by, you can see here mass is m, here c square is basically equals to this, and 2 is as it is. Okay, so you just have to put the value of this is t and this is r, and k is as it is. Just put the value, you have to put the value of v, which is this c, and this is the value of c, 3 multiplied 10 raised to power 8, because this is in denominator, you have to reciprocal mc square divided by 2e, mc square divided by 2e, and mass is separate, E is separate, and just put the value of c square, which is 931 mega electron volts per nucleon, and 2 is as it is. So this is all the way constant. After putting the constants values, you will get a new constant, which is 1.2 into 10 raised to power minus 7. Okay, so this is new constant, and r is basically the range of the particle in which they penetrate, and basically this as it is, ma, basically ma, as I told you, which is the atomic mass unit of the particle, and E is basically the energy. So this is the final relation of stopping time. Okay, the time required to stop a charged particle in the absorber. This is basically the stopping time, which is equals to 1.2 into 10 raised to power minus 7 r under root ma divided by e. Okay, so let's start next. Our next thing is we have to study the range of the charged particles. To study the range of a charged particle, first of all I have to let you know that a charged particle moving when through a certain material, it loses its kinetic energy. Okay, once it loses its kinetic energy, as I already written here, it loses its kinetic energy, okay, through the interaction with the electron and the nuclei of the material. Because when a charged particle is moving inside the material, it loses all its kinetic energy which it has initially, and after it has no energy, it start decreasing. Once it penetrate into the material, eventually all particles will stop down after some time. Okay, definitely up to necessary num of all necessary number picking up all necessary number of electrons from the surrounding material. After, when it stop, it pick up all the electrons from surrounding. Okay, so this is basically simple. Is that so? Let us illustrate with an example like proton. A charged particle is coming. When it interact with some matter having electron, it becomes a neutral atom. Okay, and neutral atom is hydrogen atom. Okay, this is another atom example, like helium atom is penetrating into some material. It pick up two electrons and becomes helium neutral atom. Okay, so this is basically simple range formula. You must have to understood that to know how to solve. So this is exponential power exponential 1.6 under root which is T. What is this T? Kinetic energy of the charged particle in mega electron volts. So this is how to find range of the particle. But this only occurs when your range must be between 1 to 4 mega electron volts. If greater than 4, then this formula violates. Okay, this formula only justify when your kinetic energy of charged particle is in between 1 or 4 mega electron volts. Okay, so what if energy is greater than 4 mega electron volts, okay, and smaller than 15 mega electron volts? A new formula, and a new formula is that 0.05 T, which is the kinetic energy of the charged particles, plus 2.85 multiplies by T power 3 by 2. Okay, in mega electron volts. This is the two formulas of finding the range of a charged particle. Okay, this is when your energy in between 1 to 4 mega electron volts, and this is then when the energy is between 4 to 15 mega electron volts. Okay, understood? Okay, so there are two different things. First is mean range and the other is exploit range. Okay, to find the mean range, there is a formula that you have to take the ratio of r1 divided by r2, which is equals to rho 2 divided by rho 1, and under the root area 1 divided by area 2. So let's take an example, so we know this how to solve a problem to find the range. Let's suppose we have to find a range. What is the range of a 3 mega electron volt alpha particle in gold? Mostly we use silicon, okay, with to comparison. Okay, in all problems we use silicon as to be comparison. Okay, so that's why we have to find r1. So r2 goes this side. This is basically r2. And what is this r2? This must be given. R2 is basically the range of some other particle. I should say that silicon. So silicon is, and this should be given 12.5 into 10 to the minus 6. This is basically the range of the silicon. Okay, and a1, because we have one thing is the au gold, which we have to find. So a1 also the what area of the gold, which sorry, atomic number of the gold, which is 197. Okay, and a2, second thing we compare with silicon, and silicon has the atomic number is sorry, a is basically the mass number, not the atomic number. A mass number 28, and gold atomic number 1, gold mass number 198. And rho 2 what is basically basically the charge density of silicon, and rho 1, which is the charge density of the gold. These all variables constants must be given. After putting the values, you will get your answer. So the range of gold is basically 3.8 micrometers. Okay, so that's all for today. In this lecture we will discuss, this is a brief of lecture number 2 of nuclear tracks, which we discussed today. We discussed today that particle and ions interaction with the medical, how particles comes with some velocity v having mass m. When it strikes with some material, it penetrates, and what is the stopping potential, what is the stopping power, what is the stopping time. We already discussed each and everything in briefly. And we also discussed the Bragg's curve, what is basically the Bragg's curve. We also discussed the characteristics, energy loss. We also discussed energy straggling, what is energy straggling, how peaks, if peak are sharp, so we conclude that they are energetic. We also discussed stopping time. We find their formula relation, how to find stopping time. You all know what is stopping time, and the time to stop a particle inside when it penetrate into the medium. Okay, and we also now discuss the charge range of the charge particle. This is all the way up. So that's all for our today's lecture number 2 of principal matters and applications of nuclear tracks. So in tomorrow's or our day tomorrow, we will start our third lecture, and we will go further and discuss about this course. Okay, so this course is very important, and from before this course you must have to know how about nuclear physics, so it's easy to you to concern with this course. Okay, this course is basically the prereq of the nuclear course. First go through all the basics of nuclear physics, then you must have to go move towards the this course. Okay, we are following a canal book, and the book is of third edition. Okay, so that's all for our third lecture, and this is our lecture number 2 on nuclear tracks. So stay tuned with us. Thanks for watching, and Allah Hafiz.